Did you know over 30% of AWS SAA C03 exam questions are based on networking and VPCs? Let's break down those exact question patterns with answers and clear explanations you won't find in dumps. A company runs an application on premises that must consume a REST API running on Amazon API Gateway. The company has an AWS Direct Connect connection to their Amazon VPC. The solutions architect wants all API calls to use private addressing only and avoid the internet. How can this be achieved? This question tests your knowledge of combining AWS Direct Connect with VPC endpoints to create a fully private connection from on-premises to API gateway. The key requirement is keeping everything on private IP addresses without touching the public internet. The options are A, use a private virtual interface and create a VPC endpoint for Amazon API Gateway. B, use a transit virtual interface and an AWS VPN to create a secure tunnel to Amazon API Gateway. C, use a public virtual interface and an AWS VPN to create a secure tunnel to Amazon API Gateway. D, use a hosted virtual interface and create a VPC endpoint for Amazon API Gateway. Think of Direct Connect with a private virtual interface as a dedicated underground cable from your office to AWS, and the VPC endpoint as a private door into API Gateway. Together, they create a completely internal path. No one from the outside, public internet, ever sees your traffic. The correct answer is A, use a private virtual interface and create a VPC endpoint for Amazon API Gateway. Why option A is correct? This is the perfect combination for fully private connectivity. A private virtual interface on Direct Connect allows your on-premises application to access your VPC using private IP addresses only. When you create an interface VPC endpoint for API Gateway, it provisions an elastic network interface, ENI, in your VPC with a private IP address. Your on-premises application can then call the API Gateway through the Direct Connect private virtual interface, which routes to the VPC endpoint. All traffic stays completely private on the AWS backbone with zero internet exposure. This setup uses private DNS names and private addressing end-to-end. Why the others are wrong? Option B is incorrect because transit virtual interfaces are specifically for connecting to transit gateways, not for general VPC access, and adding VPN defeats the purpose of Direct Connect. Option C is incorrect because public virtual interfaces use public IP addresses to access AWS services over the public internet, which violates the private addressing only requirement. Option D is incorrect because a hosted virtual interface is just a private VEF provided by another AWS account. It's not fundamentally different from option A, but this answer doesn't specify private, making it less precise. If this video is helping you, support us by hitting the like button, and don't forget to subscribe for more content like this. Next questions. An application running a private subnet of an Amazon VPC must have outbound internet access for downloading updates. The solutions architect does not want the application exposed to inbound connection attempts. Which steps should be taken? This question tests whether you understand the complete architecture needed for private subnet instances to access the internet for updates while staying protected from inbound traffic. You need both components working together, not just one. The options are A, create a NAT gateway and attach an internet gateway to the VPC. B, attach an internet gateway to the private subnet and create a NAT gateway. C, create a NAT gateway but do not attach an internet gateway to the VPC. D, attach an internet gateway to the VPC, but do not create a NAT gateway. Think of the NAT gateway as a secure courier service and the internet gateway as the building's main exit door. Your private packages instances give requests to the courier, NAT gateway, who uses the main door, internet gateway, to go outside, but strangers outside can't knock on your private door directly. The answer is A, create a NAT gateway and attach an internet gateway to the VPC. Why option A is correct? For private subnet instances to access the internet, you need both a NAT gateway and an internet gateway working together. Here's the traffic flow. Your private instance sends requests to the NAT gateway, which sits in a public subnet. Then the NAT gateway forwards that traffic through the internet gateway to reach the internet. The NAT gateway translates private IP addresses to its own elastic IP address, allowing outbound connections while blocking all unsolicited inbound attempts, exactly what the architect wants. Without the internet gateway, the NAT gateway has no path to the internet. Without the NAT gateway, your private instances would need public IPs and be exposed to inbound traffic. Why the others are wrong. Option B is incorrect because you cannot attach an internet gateway to a subnet. Internet gateways are always attached at the VPC level, not the subnet level. Option C is incorrect because a NAT gateway by itself cannot reach the internet. It requires an internet gateway at the VPC level to route traffic out. Option D is incorrect because without a NAT gateway, private subnet instances can't access the internet, even with an internet gateway attached. Private instances have no route to the internet gateway. To get the free PDF or mock test, comment PDF or mock or both. I will share the downloadable link within the next 24 hours. A solutions architect has created a new security group in an Amazon VPC. No rules have been created. Which of the statements below are correct regarding the default state of the security group? Choose 2. This question is testing your knowledge about what happens when you create a brand new custom security group, not the VPC's default security group. Pay attention to the difference between inbound and outbound rules in the initial state. The options are A. There is an inbound rule allowing traffic from the internet to port 22 for management B. There are no inbound rules and traffic will be implicitly denied. C. There is an outbound rule allowing traffic to the internet gateway. D. There is an inbound rule that allows traffic from the internet gateway. E. There is an outbound rule that allows all traffic to all IP addresses. Think of a new security group like a brand new nightclub with security guards. By default, the bouncers, inbound rules, let nobody in unless you explicitly tell them who's allowed. Everyone is denied entry. But the exit doors, outbound rules, are wide open. Anyone inside can leave freely to anywhere. The correct answer is B. There are no inbound rules and traffic will be implicitly denied. E. There is an outbound rule that allows all traffic to all IP addresses. Why B and E are correct. When you create a new custom security group in AWS, it starts with a very specific default configuration. For inbound traffic, there are absolutely 0 rules. This means all incoming traffic is implicitly denied because security groups are denied by default for inbound. For outbound traffic, AWS automatically creates one rule that allows all outbound traffic to all destinations, 0.0.0 for IPv4, on all protocols and ports. This design philosophy follows the principle that your instances should be able to initiate connections outward while being protected from unsolicited inbound traffic. Why the others are wrong. Option A is incorrect because AWS never creates automatic inbound rules for port 22 or any other port. You must explicitly add those yourself. Option C is incorrect because the outbound rule allows traffic to all IP addresses, 0.0.0.0.0, not specifically to the internet gateway. Option D is incorrect because there are no inbound rules whatsoever in a newly created security group, not from the internet gateway or anywhere else. A company has multiple Amazon VPCs that are peered with each other. The company would like to use a single elastic load balancer, ELB, to route traffic to multiple EC2 instances in peered VPCs within the same region. How can this be achieved? This question tests whether you understand the cross-VPC capabilities of modern load balancers. The company wants one load balancer to distribute traffic to instances across multiple peered VPCs, not just within a single VPC. The options are A. This is possible using the classic load balancer, CLB, if using instance IDs. B. This is possible using the network load balancer, NLB, and application load balancer, ALB, if using IP addresses as targets. C. This is not possible. The instances that an ELB routes traffic to must be in the same VPC. D. This is not possible with ELB. You would need to use Route 53. Think of IP-based targeting like having a delivery service that can deliver to any address, IP, regardless of which neighborhood, VPC, it's in, as long as the neighborhoods have a connecting bridge, VPC peering. Instance ID targeting is like requiring the package recipient to live in the same neighborhood as the delivery service. Answer is B. This is possible using the network load balancer, NLB, and application load balancer if using IP addresses as targets. Why option B is correct. Both NLB and ALB support IP address-based target registration, which allows you to register private IP addresses from peered VPCs as targets. Here's the key concept. While the load balancer and target group must reside in the same VPC, the actual target instances can be in different peered VPCs when you use IP addresses instead of instance IDs. When you create the target group, select IP as the target type and register the private IPs from your peered VPCs. As long as VPC peering is configured and route tables allow traffic flow, the load balancer will successfully route traffic across VPCs. Why the others are wrong. Option A is incorrect because Classic Load Balancer only supports instance ID-based targeting, which requires instances to be in the same VPC as the load balancer. It doesn't support IP-based targeting for cross-VPC scenarios. Option C is incorrect because modern ALB and NLB have evolved beyond this limitation through IP-based targeting. Option D is incorrect because Route 53 handles DNS routing, not load balancing across instances. You definitely can achieve this with the right type of ELB. Your company has a critical application which runs in the VPC on an Amazon EC2 instances and use Amazon S3 for storage. While PCI auditing, the security team found that some traffic is going through the internet. Which enhancement can be applied in the VPC before updating the route table to resolve this security issue? This question is about fixing a PCI compliance security issue where S3 traffic is going through the public internet instead of staying private within AWS. The auditors want all traffic between EC2 and S3 to remain on the AWS internal network. The options are A, create a VPC endpoint for Amazon S3 access. B, create a NAT gateway for Amazon EC2 access. C, create a VPC endpoint for Amazon EC2 access. D, create a NAT gateway for Amazon S3 access. Think of a VPC endpoint for S3 as a private tunnel directly connecting your VPC to S3 without stepping outside. Currently, your traffic is like leaving your secure building to walk across a public street to reach the storage facility. The VPC endpoint builds a private bridge so you never leave your secure premises. The correct answer is A. Create a VPC endpoint for Amazon S3 access. Why option A is correct? Creating a VPC gateway endpoint for S3 is the perfect solution for this PCI compliance issue. When you create an S3 VPC endpoint and update your route table, all traffic between your EC2 instances and S3 will stay entirely within the AWS network. It never touches the public internet. This is exactly what the security auditors want. The best part? Gateway endpoints for S3 are completely free with no additional charges. You simply create the endpoint, add it as a target in your route table, and your S3 traffic automatically routes privately through the AWS backbone. Why the others are wrong. Option B is incorrect because you don't create NAT gateways for EC2 access. NAT gateways are for allowing instances in private subnets to access the internet, which is the opposite of what we need. Option C is incorrect because there's no such thing as a VPC endpoint for EC2 access. EC2 instances are already inside your VPC and don't need endpoints to be accessed. Option D is incorrect because NAT gateways route traffic through the public internet, which would make the security issue worse, not better.